Okay, think back to when you first learned math. You were taught how to add, subtract, multiply, and divide, right? It was all pretty straightforward. But then you probably encountered a puzzle that looked a little something like this. A mysterious, empty box multiplied by 3 equals 15. So what goes in the box? Your brain probably jumps to the answer right away. It has to be 5. Why? Because 5 times 3 is 15. Well, congratulations. The very second you started thinking about what missing piece fills that blank to make the whole statement true, you were already doing algebra. It really isn't just rote memorization. It's honestly just an intuitive game of filling in missing puzzle pieces. Welcome to this explainer. Today, we're popping open the mathematician's toolbox and totally demystifying algebra. We are going to transform what often feels like a confusing, overwhelming jumble of letters and numbers into a highly visual, totally logical toolbox for solving real-world puzzles. Think of algebra not as some massive hurdle, but as your framework for figuring out the unknown.
Here's our roadmap for the day. We're going to hit 5 main stops. First up, the language of algebra. Then, foundational identities. After that, visualizing the math. Then we're advancing your math toolbox, and we'll wrap it all up with some essential problem-solving strategies. Let's get right into it.
All right, Section 1, the language of algebra, defining the pieces of the puzzle. So let's dive right into this foundational vocabulary, because in algebra, we're constantly juggling 2 main types of pieces. First, we have our variables. A variable is literally just a letter, usually x or n, that takes the place of an unknown number. It's essentially our empty box from earlier, just wearing a letter costume. Second, we have constants. Now, a constant is a fixed number whose value is already perfectly known, kind of like the numbers 3 and 15 we just looked at. Simply put, variables are the missing pieces we're trying to find, and constants are the reliable anchors we use to actually track them down.
Let's see what this looks like in the real world. Imagine Priya heads to the game store. Now, she already has some video games sitting at home, but we have no idea how many. So boom, that's our variable, x. While she's at the store, she buys a bundle of 5 used games. We just add that to her collection, giving us the phrase x plus 5. When she finally gets back home, she counts her entire collection and realizes she has exactly 16 games in total. So we write x plus 5 equals 16. Just by translating her afternoon into mathematical notation, we've built a puzzle that's super easy to solve. I mean, clearly, x has to be 11, right?
Now, there's a really crucial distinction we need to make here between an expression and an equation. An expression, like x plus 5, has terms separated by math operations, but notice it has no equal sign. It's essentially just a phrase. We can evaluate it if someone tells us what x is, but we can't actually solve it on its own. An equation, on the flip side, is a complete sentence. It takes 2 or more expressions and actually sets them equal to each other, like x plus 5 equals 16. It's that magic equal sign that means an equation can actually be solved. So what kind of numbers are we actually plugging into these things? Well, they generally come in a couple of flavors. We've got rational numbers, which are your nice predictable numbers that can easily be expressed as a simple fraction. This includes your whole numbers and integers. On the other side, you've got irrational numbers. These are the rebels. They cannot be expressed as simple fractions. Think of pi or certain pesky square roots. But both of them play an absolutely critical role in the algebraic universe. Okay, before we go any further, we have to talk about the absolute, undeniably most important rule in this entire explainer. The golden rule of equations. Do unto one side of the equation what you do to the other side. You see, algebra is entirely about balance. You need to picture an equation like a perfectly balanced physical scale. Whatever operation you decide to do, whether that's adding, subtracting, multiplying, or dividing, you absolutely must do it identically to both sides. As long as you maintain that perfect balance across the equal sign, you can confidently manipulate the whole puzzle to find your missing variables. Moving right along to Section 2, Foundational Algebraic Identities, the core tools in your kit. Think of an identity like a cheat code. It's a special type of equation that is always true, no matter what crazy values you assign to the variables. They basically act as quick shortcut formulas for complex calculations. And these 3 right here, these are the absolute workhorses of algebra. You've got a plus b whole squared, you've got a minus b whole squared, and the classic difference of squares. A plus b times a minus b equals a squared minus b squared. Memorizing these is literally like upgrading your math software. They're going to let you totally bypass all those tedious multi-step multiplications. That brings us to Section 3, Visualizing the Math, Geometric Proofs of Abstract Concepts. I love this part because it shows that algebra isn't just invisible magic. It's actually deeply tied to geometry. Let's prove that a minus b whole squared identity visually.
Imagine a large square with side length a, which gives it an area of a squared. Now, we want to find the area of a smaller square inside it with side length a minus b. To do this, we subtract a vertical rectangular strip with an area of a times b and then a horizontal strip also with an area of a times b. But wait, think about it. By subtracting both of those strips, we accidentally subtracted the little overlapping square on the corner twice. It totally vanished. To fix this, we have to add that small corner square back in. The area of that tiny square is b squared. So the final true area is a squared minus 2ab plus b squared. Boom! It's a flawless geometric proof of our abstract formula, grounded in physical space. All right, time for section 4, advancing your math toolbox, leveling up through the classes. Now, don't let the fancy terminology freak you out. As you progress in your mathematical journey, this foundational logic simply scales up in complexity. In earlier classes, you master exponents and polynomials, learning the rules for handling variables with powers. By class 10, you're tackling the big stuff like the quadratic formula and analyzing numeric progressions. And by the time you hit class 12, you're taking these exact same algebraic principles and applying them to multidimensional physical space using vector algebra. The core rules we've talked about, they remain exactly the same. The application just gets way more powerful. Speaking of leveling up, let's really highlight the quadratic formula. When you hit a tricky polynomial equation that looks like ax squared plus bx plus c equals 0, this formula is your ultimate time-saving shortcut. It finds your unknown x with the fewest possible steps. And a huge piece of this formula is what's called the discriminant. That's the b squared minus 4ac part tucked under the square root. Just by calculating that tiny little piece, you can instantly determine the nature of your answer. You'll know right away whether your roots are two distinct real numbers, two equal real numbers, or even imaginary roots. It's super cool. But hey, algebra isn't totally limited to infinite possibilities of numbers. Let's look at Boolean algebra. This is a specialized, incredibly fascinating branch used primarily in computer science and digital logic. In Boolean algebra, variables only have two possible values, typically a 0 and a 1, representing true or false. And because of this, it has its own totally unique set of rules. For example, the impotent law states that a plus a simply equals a. The null law says a plus not a equals 1. These rules are literally the invisible logic driving the very device you are using to watch this explainer right now. And finally, we hit section 5, essential problem-solving strategies, cheats and shortcuts. So what happens when you're staring down a massive, messy expression? Your main goal is usually factorization, breaking it down into much simpler, bite-sized multiplied pieces. Here is your systematic strategy. Step 1. Absolutely always look to take out common factors first across all terms. That is going to simplify your life immediately. Now, moving to step 2. If you have 4 terms, try grouping them in pairs to find common brackets. And finally, step 3. Keep your eyes peeled for those foundational identities we talked about earlier, especially the difference of squares method. Spotting one squared term minus another squared term is an instant shortcut for factorization. Another really major strategy is mastering proportions so you can solve complex word problems. Instead of getting totally lost in the specific letters, let's focus on the relationships between them. In a direct proportion, they move together, meaning as one increases, the other increases right along with it. In an inverse proportion, they act more like a seesaw. As one increases, the other decreases. Your core strategy here is to fix one variable, find your constant, and then just proportionately adjust the other variables to solve whatever scenario you're facing. Okay, and what about fractions? If seeing a sea of letters stacked on top of other letters makes you nervous, take a deep breath. The rules for algebraic fractions follow the exact same logic as your standard everyday numerical fractions. To add or subtract them, you still just need to find a common denominator. To multiply, you're multiplying straight across the top and straight across the bottom. And for division, you simply multiply by the reciprocal of the second fraction. That's it. It is the exact same arithmetic you've always known, just wearing a variable costume. So, we've unpacked the basic language, proved our foundational identities visually, explored some advanced formulas, and laid out systematic problem-solving strategies. You officially have a highly organized mathematical toolbox, which leaves us with this final thought. If the universe is fundamentally built on balance and missing variables, what other real-world puzzles in your everyday life can you solve using the logical rules of algebra? Keep your eyes open for those missing pieces.